Hello, hello. This is Postgres FM, episode number 101. My name is Nick Samokhvalov, founder of Postgres AI, and I thought about so since like last time we had episode number 100, and it was interesting because we discussed databases at scale of 100 terabytes and beyond. Logically, this episode should be something very simple and beginner entry level because it's 101. You know, in the US, 101 means something like some introduction to something, right? But I guess we will dive quite deep. I hope we will dive quite deep into some details of some things. Very interesting to me personally, but also like since a couple of days ago, Timescale released addition to pgvector called pgvector scale. I asked developers to join, and they agreed. So meet Matt Arieh. Hi, Matt. Thank you for
Hello.
coming. Thank you for
Thank you
coming.
for
And
having us.
John Pruitt, uh, thank you for coming as well. It's
Hey,
great
thanks.
to have you. Great to have you. And let's start. Like it's kind of interview, but maybe it will be some informal, maybe discussion because I don't know. Like we know each other for some time, and why not, right? So uh, let's start from the beginning, like from maybe some distance. Why do we need at all some vector search in Postgres and maybe some vector search in general? Because recently, not long ago, um, LLM it's becoming bigger and bigger at a very high pace in terms of how many dimensions, but also in terms of context window, right? Gemini now supports 1 million. There are talks about 2 millions. Although I must admit, Gemini is terrible in terms of reliability. We have a lot of credits being a AI startup, Postgres AI being a AI startup. We have a lot of credits to spend, and it's very well known problem with Gemini that 500 errors all the time. Like it's becoming me it's making me very sad. But 1 million context window means that probably we don't need vector search at all, and we can just put everything into one prompt, right? There was such crazy idea when context became really large. Imagine if we have like 100 million tokens context window, you can just put everything to a single question, or it's insane idea. What do you think?
Uh, I think there are a few points to point out. First of all, there's still the bandwidth that you need to use up to send the question to the LLM, right? So there is going to be a pure networking limit at some point. Um, Another point is that even with very big context windows or token windows, yes, you can give the LLM a lot of information, but there's actually an open question about whether it will use all of the information it gets well. And there's some academic research out of LLM is actually showing that giving it less information, but more relevant information in the
Mhm.
prompt is gets you better results than giving it all the information you have, right? And so, I mean, with LLMs in general, all of this is purely empirical research that's actually not very good scientific backing either way. But for the LLMs that people have tested, I know that huge prompts are often not very good in terms of performance. In terms of the answers you get. So in that sense, narrowing prompts down using either vector search or text search or hybrid search, whatever you want, in many cases it gives you a better answer. And apart from that, and this is a bit controversial, I'm actually not convinced that RAG is the killer app for vector databases. There's a lot of other use cases for vector databases, starting from clustering, recommendation engines, plain old search engines, right? A lot of other things that have nothing to do with the RAG, and that increasing context windows will not, help a hit. These are just orthogonal things. And the basic thing that what vector search gives you is semantic search. And there's a lot of applications of that.
So not only RAG, right? So interesting. Yeah, that's so okay. So your answer is like has 2 points, like to summarize. First, we still need to narrow down and find on, and if we put everything to one question, it will be not efficient. And I agree with LLM sometimes, like if you put too much information, it's answers are not good. Quality of answers decrease for sure. And second, it's not only about RAG. I would like to explore this. Like, do you see some good examples beyond retrieval augmented generation? And actually, while you think, let me just spend like maybe half a minute because I know our audience is mostly Postgres engineers, DBAs, and backend developers. Of course, many already heard about RAG, but just like small recap, it's quite simple thing. And actually, you're right. Maybe vector search is not needed in RAG. For example, we can use full text search there, right? So idea is when some request is coming to LLM, before passing this request to LLM, we have intermediate software which finds additional information which should be relevant. And here vector search can be useful, but maybe not only vector search, for example, full text search. And then we already augment this request with this information, and LLM has some context. Basically, it's similar to if you go to exam and you have a lot of information in your pockets. When you need to answer, you can get this information out of your pockets and answer better, right? So or use Wikipedia, for example, right? Similar. But you just told me that it's not only RAG. What else? Like, what else for vector search particularly?
I mean, fundamentally, I think any time that you are right now using full text search or text search, you could substitute that with semantic search to give you better results. Let me just give a simple example for people. With the full text search, searching for a query on car does not return results that have truck in the document, right? Semantic search solves that because it's kind of, I mean, that sounds almost magical, but it's kind of a search on meaning. So things that are close to getting meaning get retrieved. So you could use a totally different lexical structure, totally different word, and somehow this type of search figures out that they are similar in the meaning space, if you will.
Or you could use it
Right.
to augment full text search, or as a hybrid of the two.
Have you seen good examples of this? Like I saw terrible techniques, like for example, let's find 100 results from full text search, 100 results from vector search, and then combine them. But always I have a question: how do you what's ranking system? Because they have like it's very different, and sometimes we want fresh information. Yeah, a specific question I would like to explore maybe later, how to reflect freshness of data, right? So we can discuss it maybe later, because I also like already want to discuss, but you particular just released. But did you see any good examples of combination of full text search and semantic search, like vector search?
It's hard to say because we we are a database provider, so we kind of we don't see the examples that our customers have. We get told by our customers that, hey, this technique works, you find it useful, blah, blah, blah. But we rarely actually see the results ourselves. But like anecdotally, a lot of people are using hybrid search.
Hmm.
And like in the AI community, I think it's almost becoming the standard, which is potentially a problem for Postgres we can go into later, but that's what we're hearing at least a lot. But I will agree that this is totally all ad hoc, non-scientific, like
Yeah, it's
scratch my left ear with my right arm type thing, right? So yeah.
all like for me, it looks almost always like all examples I see, they look ugly because, for example, if you think about pagination, there is no way to have pagination there. Although if we go back to vector search, it's also problematic there because to go to page number 100, you need to extract all 100 pages, and it's very inefficient performance-wise. So let's discuss the project. It's called PG Vector Scale. It looks like you just appended suffix scale, right, to PG vector. And it's a very interesting approach because let me ask you this. It's very well known that timescale DB is a very great thing for time series. It has free version and you can host it yourself, a community edition, I think it's called. I doubt it's true open source because it doesn't have OCI approved license, right? So it's like some specific thing, or maybe Apache license exists, but it lacks a lot of good stuff. For example, I think it lacks compression. Maybe I'm wrong. Is it
Yes,
so?
yes, it lacks compression. So
Right,
we have an Apache version, we have a community version. Yes.
right. I think you can use extended version, still not paying if you host yourself, but
Yes.
it cannot be considered true open source because this license is already something like hybrid and so on. Then we have
We call it source available.
source
It's not
available.
open
Yeah,
source,
yeah,
but it
this
is
is
source available.
common term.
Yeah.
Right. So then Postgres itself has very, very, very simple and permissive license. You can. That's why many commercial products developed on top of it. And then we have PG Vector, right, which is a separate extension, which, in my opinion, should at some point go to core Postgres. But there is a big question: how come? Because it's breaking all the rules because just creating index you might have results which differ from original results without index, right? And like it's something which we didn't have before because always indexes just speeded up queries. Now we can change results because it's approximate neighbor search. But and this project I think it's on which license it is. I don't remember, but I think
Postgres license.
it's also Postgres license, right? And maybe that's why you also developed your product on top of it using Postgres license. But it's very interesting because if before Timescale had this major product everyone loved, compression especially, but only if you go that route, source available, or you go to Timescale Cloud. Now you release this thing as on Postgres license, meaning that anyone, any cloud provider, most of them already have PG Vector, so naturally they should already be considering adding your extra, right, to their services. And I think, of course, you've thought about it very well. So my question is why you changed your approach compared to Timescale?
Yeah, so I'll speak for myself, maybe not for the company. I think, look, we all love Postgres, but I think Postgres needs different things in different areas. Postgres, in the time series area, Postgres already has a lot of functionality to build in, and we already like building upon a well-known foundation where I would argue that given our broad definition of time series, in many ways, Postgres already dominates the market. So we felt that we could build a company while contributing some things to Postgres, but also, quite frankly, making a business for ourselves and making money in this area by preventing hyperscalers from making all the money off of our work, which is what the TSL license does. It doesn't stop any individual from benefiting from our work or really any company. It only stops the cloud providers from making money off our work. And that was done for pragmatic reasons so that we could make a business.
Mhm.
In terms of vector, I think the whole vector market is much more nascent and much younger. And I don't think Postgres has won the market a lot. You can look at how many other databases have gotten millions of dollars in the past year to develop their own solution. This is a very hot, fast-moving market where I don't think Postgres yet has a particular, it hasn't won, right? And so because we like Postgres so much, we
Yeah,
wanted to
that's I
help
understand.
Postgres win. And so
There are
this
many
was
there are
that
many benchmarks with where Postgres has very poor results with pgvector on if flat index without HNSW and so on, right?
I
And
will
they're
say
still around.
I will say with pgvector 07, things have improved on the pgvector side quite a lot as well. But yeah, and I think not only in terms of benchmarks, I think in terms of actual usage, if last episode that you talked about 100 terabyte databases, but we want to reach 100 terabyte databases that have vector data. We have to do a lot of work to make that happen, right? And I think
Right.
that's the ultimate goal, and there should be the ultimate goal of everybody in the community. And we thought that it was more wise to help the entire community succeed at this point in time.
Yeah, when I saw benchmarks like 100,000, 500,000 vectors, I like what's happening here? And people say, "Oh, it's already a lot." Like it's not a lot, right? If you're like you take any company, take their databases, and they have already so many data entries in their databases, and out of those entries we can create vectors usually, right? So it means that we should speak about billions already, but it's not there yet because it's problematic because vectors are large and building indexes is slow, takes a lot of time, and the latencies of search, of course. Yeah, so everything is quite slow. And I'm glad you did your benchmarks starting with 50 million vectors, already very good. And I'm super glad to hear that you talk about terabytes of data. But by the way, some people say, okay, for us, like for Postgres guys, not for timescale, regular Postgres guys, one terabyte, it's usually 1 billion rows. With timescale compression, it's many more. 1 terabyte should be like maybe tens of billions rows, right? And I know,
And over, yeah.
right. So it's different order of magnitude. But if we talk about pgvector, 50 million vectors, let's talk about like this project has two things to bring on table. Maybe let's close first with no technical question because I cannot skip this question just sitting in my head. So pgvector had if flat index originally, then HNSW was added, and I remember Neon participated starting with separate project and decided to contribute to pgvector. So now it has two indexes, and pgvector scale brings third type of index, right?
Mm-hmm.
It could be pull request to pgvector, no?
So we talked with Andrew Kane about this. The issue is that we are written in the Rust and not C,
Yes.
and Andrew thought that it would be better as a separate project, and I can't say I disagree. I think either could have worked, but I think given the language difference, it makes some sense to have it as a separate project, but we did offer to upstream.
Yeah, well, makes sense. Makes total sense, but why Rust?
Because I like to work quickly, and I thought Rust would allow me to do that more than
Mm.
more than other things. I should say I'm one of the people that worked on compression and time scale, and we did our compression system had our own data type on disk. And I remember the pain of having to make sure that the way you are writing data on disk would work very well. And the Crusoe platforms, big endian, little endian, all of these, the alignment issues, it's just a lot of double checking that you have to do to make sure everything is correct. I wanted to avoid this, and with the Rust, a lot of this could be a lot simpler. So like
Yeah, makes total sense.
yeah.
Mm-hmm. And right. So this makes total sense, but for end user, it's interesting, especially if those who self-manage. So you need to take Postgres, then you need to bring pgvector, then you need to bring pgvector scale. It's interesting. It's interesting situation, and
We
but
do have
it
Debian packages, but yes.
yeah. So this is interesting, but now I understand better. And let's talk about the index itself. So like what can you tell you what you can tell us about the index compared to HNSW? And I know HNSW is like a memory thing. This works with disk, so this is definitely right thing to do if we talk about terabytes of data and billions of rows and so on, right?
Yeah. So I'm gonna hand wave a lot here because this is like a lot of history, but it turns out for various reasons that the best way to index vector data is using a graph structure, so a graph database. So you can imagine each vector is a node and is connected to other nodes that are mostly close to it, right? And then there are some far edges. And the traditional problem in these types of indexes is getting from one end of the graph to another end of the graph. So if your starting point is very far from your query vector, which is what you're looking for, it takes a lot of hops in these graphs. And HNSW and DiskNN are pretty much different ways of solving that basic problem. HNSW solves this by introducing layers into the graph, where the top layer where you start only has long distance edges. So it kind of allows you to jump a long distance, but close to where your query is. And then you go down a level in order to make more fine-grained jumps. And there are several levels. By the time you get to the lowest level, you are kind of in the most fine-grained area of the graph. And those top levels are the things that help you solve this long jump issue, if you would. DiskNN doesn't use multiple graphs. And instead it kind of uses a neat trick in the construction to how should I put this? It puts in enough long edges to be useful. So kind of the way it constructs the graph is modified from the regular way these types of graphs are usually constructed, specifically to inject these long edges into the graph, which probabilistically allows you to jump faster to where you need to go. And this kind of flat structure is what allows you to keep a better locality of where you are. So instead of using multiple levels, the flat structure allows you to make less hops in memory, which allows this to work on disk, on SSD rather than RAM. Because
Yeah.
Yeah.
I noticed, by the way, maybe it's like side note, but I noticed you in PostgreStub you use local SSD disks, right? Not like EBS volumes. Is it like fair or like, I mean, they're ephemeral. If you restart machine, you lose them, right? So in
Well,
your benchmark particularly, I noticed this small point.
our benchmarks very concretely benchmark Pinecone against self-hosted
Mhm.
self-hosted Postgres, and the most self-hosted Postgres people I know actually use NVMEs, and they do like I mean
But not local NVMEs. I like it's still like
but
yeah,
you can do backups other ways, right?
right.
You could
Right.
you could
And
do
failover,
streaming
yeah.
replication, you could do other ways to get around this issue of things
Just
going away.
I'm just very curious, like how much it helped because of course latency is better, disk latency is better.
I can tell you it helped immensely, and I can say that we are right now actively thinking about how to bring this kind of performance to cloud as well. Stay tuned. I think we'll have some exciting stuff coming out. But yes, that's a very astute observation because, you know, quite frankly, none of this works on EBS.
Mhm.
You need the random read performance of SSDs to make this work. So by the way, I would be shocked if Pinecone wasn't using.
Local NVMEs? Hmm.
I don't know. I have no idea what they use, but I would be shocked if this is EBS based.
Hmm. And for these 50 million vectors, how big was the database? How, like in terms of
The disk and index was about 40 gigs. The entire table, I think, was around 250, somewhere between 250 and 300 gigs.
right, and machine has definitely less than that, so of course it was not cached. We do need the disk. Okay, and back to indexes, disk ANN, and I saw you mentioned in the article and the project itself, Microsoft work, but you modified this work, right? But question is like HNSW and this disk ANN both are approximate nearest neighbors algorithms. Can we say one is better than another for most of workloads and data types, data sets, or there are cases when one can win, there are cases where another can win?
At the
What do you
moment,
think?
SW index supports concurrent index builds, which could make it faster, at least for building the index.
For
That's
4 billion index, yeah. So, and yeah,
Yeah.
but for search,
For search and accuracy, look, we haven't benchmarked everything. The thing is, we have benchmarked. We've seen higher throughput and higher accuracy, or the trade-off was always kind of better than HNSW, but we haven't benchmarked everything. We've kind of concentrated on modern embedding systems. So, for example, we haven't gotten to benchmark very low dimensional vectors like 128 or 256. The lowest thing we benchmarked is 768. So a lot of caveats, and I think the space is so new, people should actually test on their own data. But I can say, in terms of search, we haven't seen where we are worse yet.
People should always test on their own data, even if it's old school full text search and so on, because who knows what you have, right?
Absolutely.
That's one thing that made benchmarking so hard, especially versus our competitors, because a lot of the specialized vector databases have very few parameters that let you actually control the index. Whereas on Postgres with both pgvector and pgvectorscale, there are several different parameters to tune the build of the index, and then also query time, plus all of the Postgres settings. And if you're self-hosting, you've also got OS and machine level things to play with. So there's just a mind-boggling number of variables you could play with if you had the time and money to spend on it.
Yeah, and in pgvectorscale particularly, I checked source code and documentation what you have so far, and I saw also like parameters you can touch. A couple of them like query time, and a few can be also adjusted during build time. What can you say about them, like some list sizes and so on? Query search list size. And during build time, num neighbors, how many neighbors? Like, do you recommend trying to tune this, or so far no?
We try to put in the small defaults. That is what we saw as the best combination, but obviously we wanted to let people also experiment. But in terms of build parameters, I would recommend keeping them as the default. The runtime parameters is really where I think people should experiment, because that allows you at query time to make the trade-off between accuracy and speed, right? And there's the rescore parameter that I think the one we recommend to actually tune. I just realized today we probably should change the default. It's pretty low. That was my fault. But that is the parameter I think people should play with.
Yeah, that one seemed to have the most impact on both speed and accuracy at query time.
Right.
Yeah.
Right. Okay. So one more question about the index. You call it this streaming disk ANN, right? Why streaming? And how does it differ from original Microsoft implementation?
Yeah. So I think both the HNSW implementation and the original disk ANN implementation, you tell it ahead of time how many things you want to return. And that just doesn't play very well with Postgres, quite frankly, because the Postgres model for indexes is Postgres, the other part of Postgres can always ask the index for the next tuple. And this is done so that you can filter your results after index retrieval. So for example, let's say I want to find the closest vectors to a given query that also meets some other criteria that belong to the business department or the engineering department, right? The vector index only fetches the closest things to the query. And then what Postgres does is that after index retrieval, it will filter out department equals engineering, right? Now, let's say your closest 100 vectors are all from the business department. That means if
It will be,
that
it will be fast.
What? That
I
means
mean,
that,
in this case, it will be fast because
right, but if
yeah,
your
so you have connection.
parameter is say return the closest 50 from the index, then no results will be returned at all because the index returns 50 results. Those 50 results are then filtered by department equals engineering. None
I
of
mean,
them
different department. Right.
yeah. And
A lot of work to be done, but zero results. Right.
exactly. And there are zero results because there's this arbitrary limit that you give at the beginning of the query to tell you, hey, retrieve this many results. Whereas in reality, Postgres has no idea how many results you need to retrieve in order to match both the query and department equals engineering, right? So what the streaming part of the algorithm does is it removes that restriction and makes the algorithm work in the way Postgres expects other indexes to work. So you could tell the index, hey, give me the next closest thing, the next closest. Actually, you could traverse the entire graph, your entire table like that. And that makes all of your queries that have a secondary filter completely accurate.
And this secondary filter, it's a different column. Like for example, text or integer, right? Or not?
Yeah, it's a different column. Often it's a JSONB, right? So you could have an article, you could have a list of associated tags with it in JSONB, and you can say, hey, find me all the articles about cars that also come from country USA, right? Or any kind of other metadata. So it's this combination of semantic and metadata set, which is actually incredibly common.
Right, but there we have usually either situation when we have B3 and GIN index, and Postgres needs to decide which one to use and then still apply a filter, or we need to use something like additional extension like GIST, GIN B3, GIST B3 GIST.
Yeah.
I'm bad with names as usual, and then try to achieve single index scan. But here it's not possible. I mean, ideal world is single index scan without additional filtering.
Yes, that is the ideal world.
How to achieve that?
Right now, none of the indexes support that. And so all of the best you can do is the state of the art on Postgres right now, and I would argue state of the art period, but we could leave that argument for another time, is you can hope that you can retrieve from the vector index and then post filter and still have accurate results.
Mm-hmm. Well,
So
I can imagine, for example, if we take this department name, put it inside this input text which builds a vector, and then additionally we filter by integer like department ID, it probably will work better in this case, right? Because
Turn the whole thing to a vector.
because first we apply semantic search involving in the query which department we want, but then we think, okay, this filter will make final like polishing, but it sounds like again like some ugly solution. So
yeah, it's
what
not only ugly. I'm actually not sure it won't work, but like using my intuition, like the department engineering in the text would kind of skew the semantics away from the actual thing in the text you're talking about. And so I'm not sure that would combine well in this kind of semantic multi-dimensional space.
I mean, you could maybe add a dimension and like synthetically set a value in the dimension to
Right.
represent
Yeah.
which department it is.
And one more dimension for time, like timestamp, because this is so natural. I'm very curious if there are some works already in this direction, because everyone needs creation time, like publication time or something for each data entry, and like I didn't see good discussions about that yet, because if you, for example, we loaded almost 1 million entries from Postgres mailing list archives, and then it started working great, but when you see some discussion from Bruce Mommsen from 2002 about something, I don't know, it doesn't. I remember just some cases. It's already not relevant at all, and you think maybe I should delete all data, but still it might be relevant. So what we did, ugly solution. We return 1,000 or maybe 5,000 results, and then we dynamically apply some score, like I think it's logarithm approach for time. So it's like we add some penalty if the article, email is very old. It quickly becomes less relevant. We just combine it with score. pgvector provides us similarity or distance, right? And this works. This works well, but sometimes you have like 1 second latency on 1 million rows data set, and this is terrible and doesn't scale. So this problem of additional dimensions, I think it's huge. We need to extend original vector with non-semantic dimensions and use them in filtering and achieve one single index scan
Yeah,
with great performance, right?
I would say that in the academic literature there is some progress being made. That there's the filtering DiskNN paper, which I believe is 2 years old, which is ancient in the space. There was another paper from a group out in Berkeley talking about building and filtering into these graph-based indexes as well. But you gotta walk a crow before you can walk. We just haven't had any chance to really implement these inside this index, but there is kind of academic work in this area.
Right.
Seems like
For this algorithm,
It
sorry.
seems like you'd be able to signal that like certain dimensions, if that's where you're putting your filters, are that they would need to be exact versus approximate.
Yeah.
Right. And do you think DiskNN approach is better than HNSW in this particular problem, or?
For filtering, yes, I do. And obviously I'm biased, but I think the simplicity of going from multi-levels to a single level really helps in a lot of these things, just because there's a lot less edge cases to consider.
Streaming
Let's not forget.
is helps as well, right?
Yeah, I think streaming was a lot easier to implement because it's a single level, right?
Interesting. Let's not forget to talk about compression, because I'm sure we need it in vector world, in vector search. We need it. And I saw in the recent pgvector, there are ideas, let's not use integers, let's use floats and so on. It's already kind of compressions, so to speak. But you talk about real compression, right? Maybe some experience from TimescaleDB extension, like, I mean, or no, or it's different.
Yeah.
Because there is time series. It's I remember articles.
Yeah.
Timescale blog has like excellent articles, but maybe it's different here, right?
I don't think I directly used any of the algorithms from the time series space for this, but the basic insight of using the statistical properties of the vectors you have to kind of make compression give you better results is exactly what led to So we have an algorithm called statistical binary quantization, SBQ, and it takes quite a simple but well-known algorithm called BQ and kind of adapts it to your data set in a better way. We have a blog post about it. It's pretty simple. It's pretty much using the means of each dimension and the kind of standard deviations to kind of better segment your space, if you would. And we just honestly we took a very experimental approach. We took various data sets and we tried different things, and this turned out that it worked. It added a few percentage points to the accuracy, which once you get into the 90s, a few percentage points is a pretty big deal. And so it's you could read about it in our blog post. The algorithm is fully explained there.
To
Yeah,
make
that's
sure,
interesting. And
though, the compression that Matt's talking about is happening in the index, and the timescale DB compression is, converting row based into columnar and then compressing each column in the heap. And so we actually tried compressing the vectors in the heap with timescale DB compression, and seemingly random vector strings of numbers don't compress very well, so that didn't help very much.
Because in timescale DB, one of the key ideas is that for time series, it's like values are changing, not jumping. How to say, so there are deltas, and these deltas are quite low, and so on. Yeah, this is what I remember from those blog posts. So yeah, for vectors this doesn't work. I understand. Okay, and for index compression, how much could we expect? How like in terms of compression ratio to achieve?
Yeah. So SBQ uses 1 bit per dimension. The uncompressed version is flow32. So it's a very easy calculation. It's always a 32x compression ratio.
Good, understood. Great. So yeah, what anything else in technical area we should mention?
I think
with the size, but it also helps with performance because you can fit
of
more.
Course,
right? So
fewer buffers to load to the buffer pool. Buffers, right? This makes sense. And you also, I remember your blog post also mentions storage costs. You compare with Pinecone in terms of how much do you need to spend each month to store 50 million vectors, and the difference is very noticeable, I would say. So yeah, this makes sense for sure. Anything else like technical stuff? Anything maybe you're working on right now?
I think for PG vector scale, that's about it. We haven't talked about PGAI, which is the other thing we announced this week.
This is a Python untrusted, so it won't be possible to run it on managed services, as I understand, but it allows you to, or it's something different, because it makes calls to OpenAI API, or right?
It does, but so with untrusted languages, you can't allow users on clouds to write their own functions. But if the functions are included inside inside an extension, that's fine.
Right.
And it's easy to see because most extensions are written in C, which is completely untrusted, right? So the entire point of the PGAI extension is specifically so that this could be run on the clouds.
So it limits capabilities, and if a cloud vendor decides, like, verifies everything, it works well, nothing like bad calls cannot be done through it. So yeah, I
Yeah.
understand that.
It's almost
But
like
it's still
whitelisting
it's
certain yeah.
interesting. Yeah, makes sense. So the idea is to make it really simple to create vectors from regular data types, just like transparently calling these like just with SQL, right? I think there are other similar implementations of this, but I like your idea of like betting on cloud providers, including this, even not providing untrusted languages capabilities. It's
Yeah,
interesting.
there are a few things that do similar things, and I was always curious why they didn't just run the Python code to do this, and so that's what we did. Like, a lot of people do very complicated stuff to get the same result. I don't know why, but
Yeah.
yeah,
I-
we'll see how it works out.
I like this approach myself very well. Like, I mean, I do it a lot for many years. Just select and it calls something externally, but of course it should be with huge warning on side. Like, it doesn't scale well because if Python call, like, you basically add latency to your queries of the primary. And primary CPU is the most expensive resource you have, right? Because if you want to generate vector, you cannot run it on replica because you need to write it,
Right.
right? So you must do it on the primary, and while this query is running, like it's primary node, and offloading this work on Python application nodes makes total sense because database like doesn't notice this at all, and primary doesn't notice. You only speak to it when the result is already retrieved from OpenAI or other LLM provider. So this is handy, but very dangerous in terms of scalability and performance and future issues, like CPU
Completely
load and so on.
Completely agreed. Completely agreed with you. And this is a way for people to get up and running quickly and
Mm-hmm.
testing and experimenting. And we do have another project called PG Vectorizer for when you need to batch things up and scale it and do it in the background. We have all of that as well. So,
I haven't seen that. That's interesting also to
yeah,
check.
Yeah,
But I will,
it
honestly,
eliminates all of that plumbing that you have to write to drag data
Yeah.
out of the database and then send it off to an API and then put it back in the database. I mean, you end up writing so much code that, when it's in the database, you don't have to do, not to mention all of the, bandwidth you're consuming and latency there. So, yeah.
Right. I remember I was copying images from to S3 in SQL, and then of course it's also like it's similar, right? You call some APIs, right, from Postgres. It's great, but it's an interesting direction, and of course with warning, it's good for start. It's good for start. It's good for sure. So great. Okay, I think I don't have any more questions. And I'm glad. I'm looking forward to trying this project. We wanted to do it before this call, like yesterday already, but we had some technical difficulties. I hope we will solve them soon and try PG vector scale on for our case. I will tell you when we have results. Thank you. So as
And
summary. Mhm.
just one more thing about that. This is a new project. We're trying to be very responsive. So if you run into any problems at all, file GitHub issues or contact us on Discord. We're more than happy and very eager to talk to anybody. This is a young project, as I said, so all feedback is very welcome.
Sure. Yeah, that's a good point. And honestly, like seeing this work and Timescale company repository on GitHub, it makes me some like good expectations in terms of if some problems are encountered, that will be addressed and so on. This is good. And what like as a summary, let's say like everyone who works with vectors in Postgres should check out this new type of index, right, and compare. And this is great. I think there are many people who do this right now, and looking forward to results in our case and other cases as well. Thank you for good project and very interesting.
You appreciate it.
Thank you. Thank you. Good luck with it. So yeah. Bye bye.